We're living on a disk, floating through space, with a tiny sun.
Hey, I'm FTFE and welcome back to the channel that does to stupidity what a number 2 pencil could do to Golden Age Green Lantern. Thank you for joining once again. I'm looking forward to tonight. My guest today had a debate with MC Toon a few days ago. I haven't watched it yet. People tell me I really should have watched it. Scott is very new to the Flat Earth, so we're going to see how this goes. He's with me in the chat right now. So Scott, how you doing?
Doing pretty good.
Thank you for taking the time to join me.
Yeah, no, I wish I had more time to go over more topics since McToon, but yeah, do whatever.
Okay, so why don't you just take a couple of minutes, introduce yourself to everyone who hasn't seen you, and give us a brief explanation of why you think the Earth is flat.
My name's Scott, and I don't know. I think the Earth is flat just because it's just like basic common sense, and like all our senses tell us it's flat. All observable evidence is. It just doesn't go. I don't know. It just seems pretty obvious to me. And then if you look into all the videos and of everything, the way they're faking stuff, I think it's I don't know. I think it's pretty obvious, honestly. It's just like I just think it's basic common sense. But,
basic common sense. All right, that's interesting. So, what would you say is the most compelling evidence for the Earth being flat?
For me, it's that we can see too far.
When can we see too far?
Just all the observations of. When on a clear sunny day, when you can see 100 miles out or whatever, and you can see some stuff you're not under the curve. And I know you like Lovers like to say refraction, and seems like that doesn't actually apply to reality to me.
Why doesn't refraction apply to reality?
Like, I shouldn't be seeing this, therefore we probably don't live on what they're telling us.
Wait, yeah, but you said refraction doesn't apply to reality. Why does refraction not apply to reality?
Not in the way that there are people using it to make mountains disappear, and that's.
Who uses refraction to make mountains disappear? See, we know refraction happens. There's tons of videos of time lapses throughout the day of the apparent position of the horizon moving all over the place. We see different positions of the horizon. We see things behind the horizon that the next day are in front of the horizon. You know, you look at these observations that you say are, oh, on a crystal clear day, we can see 100 miles and we see the tops of these buildings. But then on other days, even when it's crystal clear, you can't see those buildings. So we know that there is refraction effects going on in the atmosphere because we don't see the same thing every day. Did you agree with that?
I mean, I agree that the horizon changes, but I would say it's due to perspective, not. I mean, I do agree. Refraction plays I've seen videos of refraction. I've seen what it does, but I've never seen it lift a mountain up. You know, so that's the topic I'd want to dive into for sure.
Even though we've shown that refraction causes light to bend, so it can do exactly what we say it does.
Well, it'd be interesting to see that, like, in, you know, it'd be interesting if there was an experiment where you could show
there's lots
like
of experiments
lifting a mountain that shouldn't be there. That would be
all right. Okay. Well, maybe I can't, you know, manipulate a mountain. I don't have that, but I do have an analog for that to show you what we say refraction does. That actually does it. So let me just grab this video. Oh God, where is it? Oh, sorry, 1 sec. I appear to have deleted it. So what we claim is that refraction allows us to see further than we would based on the pure geometry of the planet, right? And that means that things that are behind the curve, behind the horizon, which is an effect of the curve, have to be lifted up by what refraction is doing, right? So if I can show to you that we can use refraction to lift things up behind the horizon of a curved object, would that be enough to show to you that refraction does what we say it does?
Well, it'd be depending on yeah, I mean, I would have to see it.
All right, sorry. Here we go. Right, so this is a video. Right, I'll talk you through it from the start so you see what's happening. So he's got this can, and on the can there's 3 bits of plasticine: yellow, red, and then greeny, blue, turquoise, whatever. So yellow, red, and then blue.
Okay.
And what he does is he places the camera behind this curved object that you just saw there. So there's going to be a clear horizon on that curved object, which is an analog to things being behind the horizon of Earth. So as we can see there, he's placed that can with the 3 bits of plasticine behind the curve, behind the horizon of this object. So we know below that green bit there's yellow and red, right? We know they're there,
right.
But currently they are hidden by the fact that there's a curved object in the way, right? Do we agree with that?
Yep.
Right, so refractive effects happen when you change things like pressure and temperature, especially when you have extremely cold temperatures near the surface and then warmer temperatures as you go up. It causes the lapse rate, which is the change in refractive effects over distance, and it causes things to rise. So what he does is he puts some liquid propane on top of here, which is about 0 degrees centigrade, and it changes the refractive effects near the surface of the horizon, and you'll see what happens. So here he goes, he's pouring that on, and as soon as he poured that on and it changed the refractive effects, it increased the amount that light is bending around that curved object. It allowed us to see that red, which we know is hidden behind that horizon, right? And he does it again. See, as the gas dissipates, the refractive effects go away. But when you have a colder area near the surface and then it quickly gets warm as you go up, that gives us this variable lapse rate. That gives us this change in refractive index, which causes the refractive effects near the surface, which is exactly what we see over cold water. Which is why all these times of being able to see too far, they're done over cold water, you know? And that's where we're going to get the most refractive effects. And this is exactly what is happening when you're looking over that cold water with that really cold and dense bit of air really close to the surface. It allows us to see over that curve. It allows us to see the things that are hidden behind the curve of the Earth, exactly like is happening here. Does that make sense?
Yeah.
Right.
Yeah, that's a...
So
Okay.
when you say refraction doesn't apply to reality, I have to completely disagree, and you understand why, right?
Yeah, no, I see that. I'm not saying that refraction doesn't exist. I just don't think it works. I don't think it's, yeah. Just don't think it does it in the large scale on certain things, but...
I mean, why wouldn't it do it on a larger scale if it does it on the smaller scale? Why, if you had that, layer of cold, dense air spread out over a large distance, would it not allow the light to bend around the curve of the Earth exactly like we say that it can?
Because it's like, let's say if you're looking across a lake or something, and there should be like, if you're looking at the shoreline across the lake, you should be able to tell that the image is distorted. That there's a part in the image that's distorted or rising up, or
Right.
And
okay. So I can
that,
show you that. Right. So if you give me 1 sec, I will quickly grab another video. So someone that I've worked with a little bit, and I still say is an excellent flat Earth debunker, and someone you should definitely check out, is a guy called Red's Rhetoric, and he did a video on Tampa Bay, and I want to show you that video. You give me 1 sec. Let me find it. Right, here we go. So he called this the blink test, and it's quite obvious why when you see it. Come on. So, he went to Tampa Bay and used the Nikon P1000 flat earther camera of choice and pointed it at the other side of the bay. So this is what he was looking at. All right. Tampa was found on horizon. So there's the picture of the camera he was using and what he was looking at. And here's the actual pictures from the camera. So this is the other side of Tampa Bay. This, buildings that you can clearly see near the surface appear slightly distorted. The layers between the each level, different, wavy, right? However, the most important thing is what happens when you compare it to a shot from closer up. So this is almost the same angle, but a lot closer to those buildings. And you can see the shoreline, there's all this greenery below it. But when you're a lot further away, like Red's was, not only are half the buildings apparently underwater, but there is slight distortions near the surface. As you would expect with general refraction. It's not always going to be crystal clear, but interestingly, the times that you can actually see the furthest is when it's really, really clear, and refraction is literally just allowing us to see further. But you do tend to get some distortion. But again, you can see quite far, but where's the bottom of those buildings in these pictures? Perspective can't explain why they disappear bottom up when you can clearly still see like the whole of the buildings apart from what's at the bottom.
But I think I've seen experiments of why perspective does explain why things disappear bottom up, but
like what?
Uh, well, that's not like the topic I want to get into. I want to stay on refraction. So, okay, so yeah, that's interesting. It's just like when what I'm trying to. So there's only one 3-minute video I want to play.
Uh-huh.
And then after that we can talk about it. Because I think he's gonna explain it. It's best to have it's nice to have visuals and all that. But if that's cool, if I could,
Yeah, you should be able to screen share.
Let's see.
Hey everyone for watching, 500 of you. You should be able to screen share. Turned on your ability. Yeah, allow participants to screen share. It's ticked. Just click the big button.
Hold on. Shit, I can't even see the top now. Hold on.
Right, let me switch over to the screen share.
All right, here we go.
Go.
Oh, is it not? It says you are screen sharing.
Yeah, you're screen sharing. I can see that.
Oh, okay.
I just had to switch over on my feed.
It's just like there's all these like when you're able to see things like. I just feel like there's a lot of ones where refraction just doesn't cut it because you can see. Shit. Is the sound playing?
No, it won't. It won't play the sound when you just play it through screen share.
Ah, shit.
But see, this video here is part of my point. All right, you can see how refraction is completely changing the position of where everything is there. Sometimes that island looks closer. Sometimes it looks further away. That's what refraction does. And that's why observations close to the surface of the Earth are very difficult to use when you don't have data about, every inch of where you're viewing with temperature and pressure and, density. It's very hard to actually say, well, what should we see based on how refraction works?
All right, yeah, so there's, I mean, not doing a good job. Let's see. Okay. So it's just like, with this one example, it's like when you're looking across a lake, and there, in this one, there's supposed to be 12 feet of curvature. So it's just like when you can see the image and when you can see it clearly, and you're saying there's 12 feet of supposed bulge of water right here. It's like, well, like there should be.
So what's the distance for that observation?
I can pull it up later. Hold on. It's just the point I'm trying to make is that it's just like when you're able to see this and you're able to see this mirror right here, it's like there should be a point in this image where there's obvious refraction. There should be some obvious bending or something. It's like,
why should there be?
A lot of them. What's that?
Why should there be?
Because it's just like when you're say that this is happening.
There are days where refraction is really clear, and what you will see will not even be distorted, and that's the days that you can tend to see the furthest, because refraction, the light is bending around the surface of the Earth, because close to the surface of that water there is a massive variance in the refractive index as you raise it in altitude. So this matches what we expect to see. It said 12 feet, so it can't be very far. And
no, it's only at 6 miles.
Well, yeah, you go 6 miles. All right, so that's less than 1/10 of 1 degree of curvature on Earth, right? And talking about feet is not the way to think about it. What you got to think about is that refraction in this case simply has to cause light to bend 1/10 of 1 degree, which is perfectly understandable when light can do crazy, refraction can do crazy things to light. It can literally make it look like you live on a dome, the inside of a dome, with it rising into the distance. Inverse temperature functions. this is not outside of the realms of what we expect to see with refraction as we understand it.
It's just like how when there's no like, I mean, like when you go back to this video, like, now where is it? It's like it's obvious there's distortion. There's like if you took a photo of this, you'd be like, yeah, there's definitely distortion there. There's definitely that. And then you go to another one and it's clear as day, and then you still say it's refraction, but there's no evidence of refraction. It's just like,
well, the fact that you can see that far is the evidence of refraction. But refraction doesn't always have to distort things. That's not what refraction does. It isn't just something that distorts things. It can just clearly make it look like you can see too far, because light is just bending around that curve.
Across the lake. Yeah, like that's
again,
like,
that's less than
actually
1/10 of 1 degree of the surface of the curve of the surface of the Earth, right? But what happens if you actually do the measurements to see if it is curved, right? That's the important thing, is when you actually do measurements. And there's a surveyor called Jesse Kozlowski who used his surveying knowledge and equipment to measure the curve over the surface of a lake and actually show that there is the expected curve that we would expect to see. You know, how do we get the measurements if there is no curvature?
Yeah, it's a hard one to believe.
Well, I always say belief is irrelevant. Facts and logic should decide your position for you. If you want to understand refraction more, I would suggest looking at the works of Dr. Andrew Thomas Young, who is the current world's leading expert in refraction. He will gladly answer an email if you send it to him and have questions about refraction. He's modeled out what refraction would look like if the Earth were flat, based on known laws of physics and the fact that he spent his entire life studying refraction. All right, I can gladly pass you his information. I've talked to him a few times, but he will tell you, as the world's leading expert in refraction, that what we see is perfectly possible with what we expect.
Yeah, if you're expecting curvature. I mean, like, I know you can do like you can. It's just when you look at it, it's like this mountain is absolutely not like supposed to be there at all. I'm supposed to assume that this is light being bent back up to my line of sight, but it does not look like refraction. It doesn't look like there's
where's the bottom of that mountain
going on whatsoever. It just looks like it's right there.
Yeah, so where's the bottom of the mountain?
Under the ocean.
Under the ocean?
Oh, because like you can't.
So behind the curve, over the horizon.
Convergence is something very, very basic.
Yeah, convergence doesn't make things disappear bottom first when you still have a massive amount of visual acuity for the entire object. It only seems to
be there at all.
According to what?
Period. What's that?
According to what?
According to your own curvature calculator.
Well, what was the height of that observation?
It was 1,000 feet at 175 miles out. Peak of the mountain is 9,400. I know you're gonna plug in refraction, but I think that's
you have to plug in refraction because refraction is the thing that exists in reality, as I've demonstrated to you. Right? You agreed with me that refraction exists in reality.
The globe, I think, but like if there's no evidence of it, you can't say it's. You can't.
What do you mean there's no evidence of it? The fact that you can see that far is evidence of it, and the fact you are looking for it. Right, here's the thing to understand, Scott, is that refraction is happening all the time, right? This is something that blows flat earthers' minds, but it's a fact. Hold your hand up in front of your face and look at your hand, right? You're not exactly looking at your hand. You're looking at a refracted image of your hand because the light that has bounced off of your hand has had to travel through a medium to go to your eyes. And if something travels through a medium, if light travels through a medium, it's subject to Snell's law, to the laws of refraction. So whatever you look at in the world, if you are in an atmosphere, anything that you are looking at has been refracted. For me, even more. See these glasses? All right? These are, the reason I can see is because we understand refraction enough to adjust the light coming into my eyes so that I can see. Without our understanding of the laws of refraction, I wouldn't be able to see.
So you're saying that the light that we're seeing is always bending.
If it's going for a medium, it has a refractive index, right? And refractive index means that the light will not travel in a perfectly straight line.
It's like if you're like, how can anything like, how would someone, fire a missile at something 20 miles away if they have no idea what they're looking at because it's all refraction?
Because we understand refraction, and we can do ranging in other ways.
I don't think missiles.
We know distances, right? We know how far away things are. So if we're firing a missile and we know we're a certain distance away, then all we have to do is, target something that we know is a certain distance away and fire it there. We don't always need to be able to see it. In fact, you can barely ever see what you're firing at.
Yeah, it brings me back to it's just what you're telling me goes against basic direct observation, and that's why it's hard to.
In what way does it go against basic direct observations? It matches basic direct observations. I have shown you an observation that you can.
There.
No, I didn't tell you your hand's not really there. I told you that you're not seeing the exact position of your hand at that moment in time, because there's two things happening actually, Scott. One thing is that obviously the light has had to travel through the medium, so it's been refracted. But the other thing is that means that the light has taken time, all right? So even if your hand is this close to your face, you're looking at your hand refracted and slightly back in time, because the light has had to travel from one position to another. So you're never, in a sense, seeing things exactly as they are in that moment in time, because that's, how seeing works. But if it's going for a medium, it's being refracted.
It just seems like a lot of things wouldn't work if that was reality. Like we wouldn't be able to, you couldn't trust anything, any significant distance.
Even if we understand the laws of refraction and we understand what refraction does and what we expect to see, and we can model and predict those behaviors.
Yeah, it's hard for me to believe that like the military are taking into account refraction when
Scott, that's something called personal incredulity. It's hard for me to believe. I am ex-military. I am from the Royal Navy.
Okay, there's no way that's happening. That's just not a thing. Like missiles are old.
You're saying that, okay? But I was in the Royal Navy. You think when I was a submariner, actually, and do you think as a submariner we were able to see the things that we were firing at? Or did we use things like known position of things based on distance and satellite locking and GPS, And our instruments on a submarine account for the Earth being a globe. In fact, the navigation that we use, accounts for the Earth being a globe. When I was doing my training as an artificer, and my T-boat had recently gone for a refit, and we were testing the emergency diesel engines. So my job that they gave me as the artificer was to calculate the fuel needed to go from point A to point B in an emergency case of our nuclear reactor breaking down and we had to engage the diesel emergency engines. We have to know how much fuel we're going to need to get from point A to point B, right? So I did those calculations based on known distances to get from point A to point B, and then we did the simulated drill and we used the fuel that I calculated and it was the right amount. And those distances that I calculated were based completely on a globe. In fact, the Haversine formula was part of those calculations, which is something that requires the radius of Earth. So navigation that the military uses, as well as missile acquisition and stuff, uses instruments that are all based on a globe.
I mean, I would absolutely agree that that's exactly what you were taught, and that the measurements did work out, and you were thinking that it was a globe, but
if the Earth wasn't a globe, then the calculations I did wouldn't have worked, and we wouldn't have had the correct amount of fuel to get from point A to point B. But they did. They worked, and I based them on a globe. And from the point we engaged our engines to the point when we finished the drill, the amount of fuel that we used and the distance we covered with the speed that we were going exactly calculated to what we expected with the Earth being a globe.
Yeah, I mean, but how do you know that it's not a flat Earth map wrapped around a globe?
There's no such thing as a flat Earth map. We literally use the globe to navigate with the distances that the globe says. You know, we don't take a flat Earth map and navigate for that. A submarine will literally use a globe as its method of navigation and maps based on a globe. And if there is projections, then you have to do calculations to reverse those projections so that it works on a globe. There is no navigation on Earth anywhere today that uses anything other than a globe for navigation.
Okay, I just have one image. If I could pull it up, it'd be awesome.
Yeah,
so
sure.
we talk about it's about exactly this. Sorry, I don't really share screen. Okay, you see this map?
Yep, give me 1 sec to get it on the screen for everyone else. Oh, come on, computer. Yep.
So this was the map like the Air Force used in the 1953. And I know when you read the sign, like the bottom little thing, it's like we drew all the flight paths in a straight line to avoid confusion. But to me, when I'm looking at this, I'm thinking you got the North Pole in the center. You don't have Antarctica. This is for the Air Force. All the flight paths are in a straight line. This map is called an azimuthal equidistant projection map. Okay, and it's centered around the North Pole, and it's a projection based on the lines of latitude. Instead of when you go south of the equator getting smaller again, they continue to get bigger. And I can debunk this as an accurate map with one word, and that word is Australia. Because I can guarantee you, Australia does not look like that. Australia is not 4 times as wide as it is tall. Well, also, but hold on, but 1 sec. I mean, you can say that, but I mean,
it's
like,
not.
All maps
it's been
are
measured.
Ridiculous. Like Greenland is probably a much more accurate size on this map than it is.
Yeah, it is because the closer to the North Pole, the more accurate size of countries you're going to get, right? Now, the distances north to south on this map remain correct. So if you were to look at Australia and to go from the south of Australia to the north of Australia, that would be correct. But the distortion of this map lies in the east to west. And as you get further south, the distortion gets more and more and more. This was a map designed by someone called Alexander Gleason, and in the patent for the map, which was done through the US patent system, he describes how he distorted this map from that of a globe. So the person that actually made this map, the azimuthal equidistant projection centered on the North Pole, said himself that it's a projection of a globe, and here is how it is a projection of a globe in the patent for it.
Yeah, we have to understand from a flat Earth perspective, with the controlled narrative, they're not going to be like, well.
Oh, no. Alexander Gleason was actually a flat earther. And he still said in the patent for this map that it was a distortion of a globe.
Well, if he's a flat earther, why would he say it's a globe?
Because that's the only way you could get it to work. The only way he could get this azimuthal equidistant projection map to work was to take a globe map and distort it. He was still himself a flat earther. But even as a flat earther, he couldn't have a map that was an accurate representation of a flat earth. He had to distort a globe to get the map. And the Air Force would take this map and know that it is the azimuthal equidistant projection and reverse engineer it for distances, because the Air Force couldn't look at this map and go, well, I want to fly from East Australia to West Australia. Let me go and fuel my plane to make sure I got the right amount. Because that wouldn't work. Because, again, Australia doesn't look like that.
Doesn't look, yeah. I mean, you just gotta understand, like, from someone that's not a map maker, this looks like when you look 1940s, they assume they used the flat Earth map. 1950s using the flat Earth map for aviation. You're like, well, all right. You like maps, you know.
Again, it's not a flat Earth map. It's an azimuthal, extra-distant projection of a globe. There is no such thing as a flat Earth map. And they would use this knowing it's a projection. In fact, in the top right there, it's the explanation of the projection of this map. This map is made of the North Polar Azimuthal Equator. Okay, dude, literally, in the thing that you are showing on the screen, it explains how it's a projection of a globe.
I know. I've
Well,
read
there you
that.
go then.
Yeah, no, it's like, but you like if you read it from a different perspective, you're like,
Oh,
well,
if you read it from a perspective of wait. So the only perspective you should care about is the things that they say, and they are directly telling you that this is a projection of a globe. You know, they are telling you that, so you can't use this as evidence of the flat Earth.
You believe that the government is lying, so you're not going to just be like, oh, there's a little side note that says the Earth is round. I'm going to go back to the globe. You know,
no, they're explaining that it's a projection of a globe, and that was there in the 1940s on this map that people used, because they had to know it was a projection of a globe because they couldn't use this to accurately get from point A to point B. You understand that, right? That this map would be useless to get from point A to point B. You couldn't use it for that.
I mean, I wish. I mean, I've been working a lot these last few days. I wish I had more time to go over this stuff, but that's just something I found that I thought was pretty interesting.
Yeah.
That's all.
So, yeah. Projections of a globe, you know, the only accurate map that exists, the only accurate map that can be used for navigation without any kind of distortions or projections is if you use what the globe says. You know, that's the only thing in the world that has accurate distances of every country. And I've tested that.
Yeah, I mean, there are a lot of pilots that say otherwise.
Every single pilot that has to plan a flight route, every single pilot that has to plan a flight route uses the Haversine formula. It is part of their flight route planning. And the Haversine formula includes the radius of the Earth as part of its calculations. In fact, the Great Circle is, you know, what happens when you use the Haversine formula to calculate your routes. It shows that the quickest point the quickest thing to get from point A to point B happens to be a curve because the Earth is curved.
I mean,
aircraft instruments, like a fiber optic gyroscope, right? Modern aircrafts have 3 of them, yaw, pitch, and roll. Measures them each, and when they turn them on, because they literally sense the rotation of the Earth, they can determine where they are on Earth. And if what the instruments determine doesn't match what the flight data says, then you can't even turn on the plane. You know, because we can measure the rotation of the Earth because it's a sphere that's rotating. I've measured the rotation of the Earth myself.
Yeah, it's yeah. I wish I spent more time listening to the pilots and people explaining the map, but that's all I got right now.
So,
but yeah, it just, I mean, a straight line does seem like a shorter distance, but I don't know.
Okay, so is that what you would say is your best evidence of the Earth being flat?
No, definitely not the map stuff, but I mean, I think when you look at a picture and it's just like refraction, like to me, if like it really does seem like refraction does not pull up mountains. It does, like, in that if there's no evidence of distortion and
I explained to you there isn't always going to be distortion. We had that discussion, Scott.
it's just okay. But if you're 6 miles across a lake and someone tells you, "Oh, did you know that there's actually water in front of us and we can't actually see that?" I would be like, "What are you smoking, dude? Like, that's fucking ridiculous." Of course we can see it. Like, isn't line of sight a straight line?
Oh, brilliant. Okay, so you want to talk about line of sight. That's an excellent segue into one of the best evidence that I like to use for the Earth not being flat. So, the best way to avoid the extreme refractive conditions of being near the surface of the Earth is to move away from the surface of the Earth. And here we have a camera that's at 210 meters above the sea level. Right? This is actually just down the road from me, up a hill. This is a screenshot from a video a friend of mine called Miles Davis did. Not the jazz musician, a different Miles Davis. And he's next to a surveying plaque that says that he's at 210 meters. And those bridges that he is looking at are the Forth Road and Rail bridges. The red line intersects with the middle tower of the new Forth Road Bridge. And according to the engineering specifications, the top of that tower is 210 meters above sea level. The exact same height as this camera, right? So you've got a line of sight, okay? This is your eye level, right? Perspective says that parallel lines don't intersect. So perspective would never, in this case, make things fall below that red line if they were more than 210 meters. Would you agree with that? They would sink into that line, but never fall below it, because that's your eye level.
Yeah.
Right, cool. So anything that is taller than 210 meters, which is your tangent line of sight at this point, your eye level, will never fall below that red line, okay? Now, the interesting thing is those hills in the background, which are just east of Edinburgh, are about 500 meters above sea level. More than twice the height of the top of that tower. And more than twice the height of the camera, right? As you just agreed, perspective, when you've got an eye level, things will rise up to that eye level, and if they're below it, and things above it will rise down to that eye level. Just like if you're looking down a long corridor, the things above your eye level will never go below your eye level, and things below your eye level will never come above your eye level, right? So that presents a massive problem for the flat Earth here, because those hills are twice the height of your eye level, yet they have fallen significantly below the 210 tangent line. What's your thoughts on that?
This is actually pretty interesting. It's rare you get good observational evidence from the globe, so that's pretty good.
Interesting thing is the video this is taken from. He spins 180 degrees and looks in the opposite direction, and there's an even better observation. There's Hopetown Monument, which again is 210 meters, and then you can see the Perthshire Hills in the distance from that, which happen to be 1,000 meters above sea level. They're like a kilometer, but still they fall below this eye line, which doesn't make sense with the known laws of perspective. Flat earthers are always banging on about how if you look down a long corridor, the things below your eye level will rise up and the things above your eye level will rise down, and they go to that convergence line. Well, in this case, that convergence line is that red dotted line. So this picture is literally impossible if the Earth is flat.
Yeah, that's one I'd want to look into for sure. That's pretty cool.
Just blew your mind a bit there, didn't I?
A little bit. I mean, the only thing in my mind is like, well, I've seen things that are literally impossible on a globe, so I have to compare the evidence. But yeah, it's good. It is really good. That's fun.
So, have you heard of Mr. Sensible?
I've heard of him. I don't think I've ever. Oh wait, I think is he the bald guy?
Yeah, very very bold. Likes cheese a lot for some reason.
Yeah, he's I haven't really listened to him at all.
So he did a project called MAGE, which stands for Mission Above Globe Earth, where he sent up a camera. Well, he sent up 3 cameras actually attached to a weather balloon. 2 fisheye lenses, one looking at the balloon, one for the nice view, but one rectilinear lens. One lens with like the minimal fisheye distortion. And he had two reference strings on it in front that were tight to show anything in between would be, would be flat when looking at it. And at about 36 kilometers above the surface of the Earth, he took this picture.
Yeah, I think I've actually seen that video of what wasn't it like, what was it called?
MAGE, Mission Above Globe Earth.
Yeah. Oh, I think there's parts that look flat and parts that kind of look curved. But
yeah. Now here's obviously, like I just said, there were three cameras on that video, on this payload, and I'll bring up the video so you can see, and I'll show you. Oh, I've lost that. Where's it gone? Here's Mr. Sensible with his Mage project, and here is the project. Here is the payload. This camera at the front is the one that is non-fisheye, right? And it's looking through here, and in front of it over here, there's two strings, which you can see when it turns around. You see there's two strings there, right? They're straight. Yeah. So if they're straight, on the video, anything in between them is also going to be straight, right? This camera was not fisheye. But there are two other cameras on here. They're not actually in the payload right now, but one goes in this little hole at the bottom, looking out the back, and one is looking straight up, right? And here we can see all three cameras in action. We've got the one at the front with the two strings, and on the top left is the first fisheye, which is looking straight up at the balloon. And the second fisheye, like I said, the one at the back there, looking out just for the pretty view. Right? So we can't use either of these two for judging what the Earth looks like. The only time we can use this project is if these two lines are on the screen. Right? Throughout this particular video, he changes the position of the cameras. So sometimes the main one shows that it's concave or whatever, but whenever these strings are on the screen, that's the main camera, that's the one we're looking at. And at no point ever does, when the strings are there, does it look flat or distorted or anything. It shows as it is. Even when it's above the string slightly, there's still a curve. Even when it's below the string slightly, there's still a curve. The most interesting thing is they actually took the projections of what you would expect to see about this height and overlaid it. Let me play it. It should be about here. And when you overlay the projections of what you expect to see, you find that it actually matches what you saw in reality. Come on, play it. Put it up. I'm going to turn it off because I'll miss it. Oh, where is it? Ah, it's over here. There we go, yeah. So there's the projection of, the prediction of the curve, of what we'd expect to see. It's about, the prediction here is from about 2 kilometers higher, roughly, but it pretty much matches what he got. So that's what we expect to see. It matches what he actually got. Also, it manages to show us how there's a gradient to our atmosphere and lots of other good things, but definite curve to the Earth there, wouldn't you say?
Yeah, I mean, I think I watched this video a little bit, and I think I saw like someone post a picture of showing it perfectly flat at both, on both lines at one point, but
I mean, that literally doesn't happen. I promise you. The entire unedited flight's available on his channel as well.
But you also said it's like impossible not. It's really hard to get a camera that doesn't have any kind of fisheye.
Yeah, that's why we put. I mean, that's why he put these reference strings on it. Because even with a camera that says it isn't fisheye, there's going to be a bit of barrel distortion, right? But barrel distortion won't be like right in the middle. Barrel distortion would tend to be above the middle or below the middle, which is why he had this middle bit as the reference. And we saw that before he put it up, those strings are straight. That's what we're looking through.
Okay, well, something I thought was interesting to put what that picture you were just showing into perspective is when, what happens when you in certain times, like you were mentioned, like boats rising like way high, like boats appearing to be way higher, and like a missing, looks like boats are floating in water and stuff like that.
Yeah.
Well, it's interesting. Well, there's like a video when it showed like when you get a water level out, like sometimes it can show you what the horizon is like where the horizon actually is compared to what's beyond our perspective. So it's like we might be able to see farther. That might just be you know what I mean? Like that's just like that's probably the limit of our perspective is to see that far, and it might actually
Limit
even go
of our
farther out.
perspective. What does that mean?
It was just like there's just a limit to how far we can see until things converge into the vanishing point.
Why is there a limit to how far we can see?
Well, I think there's the reverse. I mean,
The inverse square law.
yeah.
Yeah, so the inverse square law would never reduce to zero. So the inverse square law tells us we can see forever. Because as long as, well,
We
2
can't
or
look
3
forever.
photons of light hit your eyes,
You can't see
then,
forever through an atmosphere, through a thick atmosphere.
well, of course there's
Cloudy,
going
you can't
to
see forever.
be, but there's no reason why on a clear day you shouldn't be able to see that far. But
Well, there's always some degree.
we're talking about convergence and stuff in the distance you can see. There's no reason why you just can't see forever in general, because that's how seeing works. And the inverse square law shows us that we would be able to see infinitely if there's a light source and at least a few of those photons hit our eyes, then we can see it.
Well, there'd have to be a powerful light source to see it, though, right? Like,
Well, our eyes in perfect conditions can detect 2 or 3 photons hitting it, right? And that's hardly anything.
If I got a super dim flashlight and went up 100,000 feet, you're not going to see it, right?
There'd be a lot of other light around, right? But have that super dim flashlight in complete pitch darkness, then with the right equipment, you're still going to be able to detect that light. As long as the photons don't just stop traveling for no reason.
Yeah, it just seems like when the idea of being able to see a star that's trillions of light years away.
Stars are really big and really, really, really bright.
That's what we're told. That's what we're told.
I mean, they would have to be. It's nuclear fusion that powers them, and you can't have small things.
Yeah, I mean, that's what they would have to be if we could see them.
Well, they are. We know they are. Spectroscopy tells us that because we can literally look at the byproducts coming from the star. If there's nuclear fusion going on at the core, that means that you're fusing 2 heavier elements into 2 lighter elements into a heavier element, right? But you don't just get that heavier element. You get bits left over, which is put out in gamma rays, in other types of radiation, light, energy, heat. That's why the sun does what it does, is because when you take those 2 hydrogen atoms and fuse them into helium, there's bits left over which are put out as energy. But we can look at that energy that's coming with spectroscopy, and we can determine that they are the byproducts of something. And we can look at the light coming from the sun, and we can tell that light is the result of nuclear fusion.
It's just, I don't know anything about spectroscopy.
Spectroscopy. I had to practice saying that, don't worry.
Does it only apply to stars, or does it apply?
No, spectroscopy is the study of light interacting with matter. Or just, not even just visible light. It's electromagnetic waves interacting with matter. So two things happen when an electromagnetic wave hits matter. You either get it to soak up that energy and emit light. That's called absorption. Or if a bit of matter just emits the energy, creating its own electromagnetic energy that comes out, then that's called emission. And spectroscopy is the study of the interaction of electromagnetic energy and matter. That's all it is. It doesn't have to be just stars. we use spectroscopy and our knowledge of spectroscopy for things like MRI spectroscopy, magnetic resonance imaging spectroscopy to look inside the brain and stuff. And it's our understanding of the interaction of light, electromagnetic energy and matter that is spectroscopy. And that's why we can tell when we look at the light from the sun, we know what that light, we know the interaction, we know the energy waves coming from the sun, and that tells us what what they are byproducts of.
So if someone went up really high into the atmosphere and they didn't tell you they were gonna give off some light source, but they didn't tell you what was causing the light source, you'd be able to determine what it was. If they were like
within a margin of error, of course, you could, if someone shined a basic flashlight at you, you could measure the wavelengths of light coming from that, and from the interaction of matter, you can tell how much energy the wavelengths are putting off because of the matter they hit. Then you'd probably be able to determine that that's coming from a simple flashlight with a luminance of whatever, But then from our sun, we don't just see light. We see heat, we see radiation, we see gamma rays, alpha radiation, beta radiation. We see other things than just light, visible light. And because we see those other things, we know that means it's byproducts of nuclear fusion.
I mean, that is pretty mind-blowing if we're capable of doing that.
I mean, like I said, there's many applications. If you want to go into a home improvement store, right, and get some paint to match your couch, right, they will use spectroscopy to make sure they get the right color paint for you. They use spectroscopy to measure the color of your couch and match your paint with it. It's our knowledge of spectroscopy that allows us to do so many things in the medical industry to the home improvement industry.
Yeah, I just wonder if it works at a distance, like
why wouldn't it?
Like at 100 miles, a certain distance where you would have to determine what it is, and you did not know what was going on. Like, I feel like that'd be pretty. Yeah, I don't know. I just don't know enough about it. Sorry.
It's all right. There's lots of nice studies of spectroscopy that you could look at that aren't too taxing. I mean, I don't want to be rude here, Scott, but I think you're a flat earther because you don't have a knowledge of physics. Right? And I don't want to be nasty, to say it, but you're ignorant of things that we should expect with the known laws of physics. If you understood what we would expect to see, then you wouldn't be so confused about being able to see a bit further than basic geometry dictates.
Well, really the question, the thing that I'm trying to figure out is if that's really the case, or if it's people that are expecting to see things because they've went to indoctrination school for 25, 30 years, and that's what they were told to expect to see.
No, see, school doesn't indoctrinate you. Education gives you the tools to think for yourself. As with a degree in physics, I wasn't just told to read a book and believe what I was told. I was given the tools to figure shit out myself. That's what education is. It's not, you're not just told this is what it is and you will believe it. Well, at least not in the schools that I went to anyway. I know there's more religious education.
I mean, that's exactly where I'm at. You're telling me stuff and I'm like, well, that's really interesting. I'm
not telling you to believe me. These are things that you can go and check yourself. Go and have an email conversation with Andrew Thomas Young. Any questions you've got about refraction, anything at all, he will gladly answer you. You don't have to just come and talk to me. I'm not an expert on refraction. Most of what I know about refraction I've picked up from doing these debates. But I'm also going to listen to the experts that have spent their life studying refraction. And Andrew Thomas Young doesn't care what shape the Earth is. He doesn't care if it's a globe. He knows it's a globe. And his studies in refraction can actually prove that.
Yeah, I mean that's what I mean, but that's what exactly I'm. You go from commenting in Facebook chat to being like, give me a good example of refraction. Tell me how this mountain isn't really there. And
Well, I did show you how that happens. Obviously, I don't have. Obviously, I don't have a mountain and the ability to change refractive conditions over hundreds of miles. But I did show you a small-scale experiment that demonstrates what we expect to happen, things being risen behind the horizon. Now, obviously, in what I showed you, there was a lot of distortion because there was a really big lapse rate. But, refraction doesn't have to create distortions. I mean, if the refractive index makes the curve of the light match the curve of the Earth, you could technically see forever, Yeah, I mean, fog and stuff withstanding.
It's just like if refraction does end up being like let's say hypothetically that globers are completely wrong when it comes to refraction and does not do, just hypothetically, like if that's true, then like the entire globe is done.
Yeah. So I mean, you're right. If refraction doesn't do what we say, then the Earth isn't a globe, right? But the thing is, refraction's been quantified for centuries. Do you know who the first person to really study refraction was?
I'm not saying it doesn't exist. I'm just, you know what I'm saying. But
no. It's not about existing. It's about our quantification of it. And do you know who the first person to really study refraction was?
No.
It was Isaac Newton. The same guy that came up with the universal law of gravity. He spent a massive portion of his life just studying how light works. And gave us a lot of what we understand about refraction. And that was centuries ago.
Yeah. Yeah, it's just interesting questioning people that do know their stuff, because it's a fascinating topic.
I mean, I've done over 630 debates. So, I mean, I'm quite versed in the things that I talk about. And there is one question that I ask every flat earther, and it's a very simple question, and that is, why is there not a single measurement of the Earth being flat or stationary?
I mean,
because there isn't. There simply isn't. But there is.
It goes back to what we like. The first thing we brought up of being able to see too far indicates that it's not.
That's not a measurement. That's just an observation, whilst ignoring the variables.
Although like even
surveyors,
to me, let's say even for me, like I would just say, well, we don't feel any motion, we don't experience any motion, we experience a stationary level. You don't experience the winds moving at 1,000 miles per hour. The
winds wouldn't move at 1,000 miles an hour. That's a straw man. Right, so let me ask you a question, Scott. If you were in a truck, right, but imagine it's the smoothest road ever with the smoothest tires ever, and it's going in a completely straight 150 miles an hour, right? And you're in this truck in the back, and you're just in a box in the darkness, right? There's no bumps in the road. There's no sound from the tires. Would you know you were moving?
If
you were going in a constant 130 mile an hour straight line, would you know you were moving? Or from your reference frame, would it seem like you were stationary?
People get car sick. They don't really think about it. I mean, you can kind of feel when you're moving.
You get car sick because of the constant little adjustments, right? And you've got fluid in your inner ear, which controls your balance and stuff. And with those, when you're sitting in a car, in reality, there's bumps and shit in the road. You're constantly, doing micro adjustments, and you get car sick because the fluid is constantly moving against your equilibrium, right? But if you were to eliminate those bumps, eliminate those movements, all right, and just imagine that it is completely like frictionless, just going 130 miles an hour, constant. You couldn't hear anything. There's no bumps in the road. There's nothing, and you're just in a black box. Would you know you were moving?
It's possible I would not know.
Exactly.
But we're not only moving in one direction. Like we're spinning, orbiting, being pulled by the sun.
Yeah. And
So that's multiple directions.
And all those directions are
all that's
constant.
one
They don't change. And the forces, what you got to look at is what forces are actually being applied. You know? And the fact that we are going fast in one direction doesn't apply a force to us. The things that apply force is gravity and centrifugal force. You know, those are the things on Earth that we can measure. We can also measure the fact that we are moving. You know, but when you calculate the forces that are being applied to you with all these movements, you know, you actually see that there's nothing that makes you feel that movement. Well, what you feel is acceleration. You feel a change in movement, right? And we aren't under massive amounts of, you know, change of acceleration all the time. It's constant what we experience.
Yeah, you know, like, it's hard to trust, like, it's like trusting a math equation or you know, over like what we observe.
Trust me, as an engineer, I trust math equations.
Yeah. I mean, there's certain things that we know the equations work out, and then I would say the math, you know, that you can make the math work out even though it doesn't. When it doesn't
you can't. If things don't actually work out, you can't make the math work because the math is based on reality.
I just saw a video of this guy, and he's like, I measured the distance to the ISS, you know, doing these calculations. And
was that Red's Rhetoric as well?
What's that?
Red's Rhetoric did that, yeah.
Yeah, and then this random, I don't know his name, it's some nerdy dude. He put in a completely random number on one of the calculations, and it came out the same answer. He's like, type in any random number in this value, and you're going to get the same answer. So it's like, I feel it is possible.
That doesn't work when you manipulate the actual variables to calculate the distances. That's not. You would have to change several things. And you're talking about Jeranism trying to debunk Red's Rhetoric, which he completely failed to do, because
it wasn't Jeranism. It was someone else. But yeah.
Well, it was probably based on the same thing. What they did was they changed the distance of one of the sides of the triangle that Red's created, whilst ignoring the fact that the distance between the 2 points didn't actually change. You know, you can't just change the angles of a triangle, but they tried doing that without actually moving the positions of where the people would be. You know, if you base it on the actual data in reality, you can't just change the numbers and make it work. But you can literally measure the distance to the ISS. And funny enough, when you do that, you get what NASA tells us.
Yeah, I just feel like it's entirely possible to have equations work out that, I mean, like, if you have math equations that work out, but you can't back it up with, not saying all the topics, but there seems like a lot of topics where there's just no way that you can provide like allow someone to observe it and look at all the factors involved and be like, okay, yeah, this is definitely, like, does it really stand up to the scientific method?
Give me an example.
Gas pressure not requiring a container. Like, you can't observe an experiment.
What are you on about? Gas pressure not requiring a container? What's that? I don't understand. What's that to do with Earth?
So it's known that gas pressure is what causes gas pressure.
It's known that gas pressure is what causes.
No, sorry. It's a container that causes gas pressure. And so our atmosphere, there's atmospheric pressure. The atmosphere is made of gas, so there's gas pressure in our atmosphere. How do you have gas pressure in our atmosphere without any form of container?
We don't have gas pressure. We have a gradient of pressure. There is no point where the pressure ends, right? What we have is, at the surface of Earth, there's 14.7 psi. Slightly above that, it's a bit less psi. And above that, it's less psi. And that just keeps going. There is no gas pressure next to a vacuum. You know, there's just a gradient of pressure that keeps going.
But Space is a vacuum.
No, space is a extremely low pressure area. There is stuff in space, therefore it is not a vacuum.
I've never heard that. I've never heard space not being a vacuum.
Well, that's the problem, is that you're ignorant of the actual facts. You've listened to the you've listened to the colloquialness of the vacuum of space, but there's no such thing as a perfect vacuum. Even in intergalactic space, between the galaxies, there is gas. There's like 0.004 hydrogen atoms per mile cubed, right? There's so little gas that there isn't even one atom in a mile cubed of space, right? But there's still some gas there. There is no point in space where space is a complete vacuum. That just doesn't exist. And all of the pressure in the universe, all of the gas in the universe is contained in the universe. So if you want a container, the universe is that container.
I mean, yeah, well, then we don't know how big the universe is. Keeps on.
No, we don't. We've got an observable like 98 billion light years.
Like,
but, you know.
The back to the main point was that like like you can't have high pressure next to a low pressure. The gas will disperse.
Well, explain our atmosphere then that has high pressure next to low pressure. You realize that as you climb a mountain, the pressure decreases, right?
Yeah, just like
so why is that high pressure lower down not dispersing?
Because there's a container.
Where? Wait. A container would stop a low pressure going to a high pressure within that container. Did you listen to what you said there? Right. So let's assume for a second, right? Work with me. Let's assume for a second that the Earth is flat and in a dome, right? Okay? In reality, we know that the pressure decreases from 14.7 psi to, as this shows, like 10 to the negative 17 torrs. You get higher and higher and higher, right? So if there is a dome container, why is there that gradient of pressure?
I mean, there's like a, I mean, this is just they're like, you can like look at a density column, you know.
Exactly. Why is it denser at the bottom? What's causing that? That is a gradient. Yeah, but why? Why is it arranged in that direction? And why, when you remove a downward acceleration, does that density column disappear?
Well, when you remove the downward acceleration.
Yeah.
When you go down with the.
Yeah.
I mean, okay, hold on. Okay, so, I mean, I think you asked a few questions there. Hold on.
Let's stick with the first one. Let's stick with the first one, right? Why is there a gradient of pressure? What causes that gradient? The air, you know, it's all the same stuff, right? So why is it more dense near the surface than compared as you go higher up?
Because when we observe objects, like the denser objects go down, the less dense objects go up. If you do observe a density column, they find their medium of density.
Yeah, but air is the same stuff, right? This air isn't more dense than this air, right?
Well,
but this air up here is less dense than this air down here. What causes that? What causes the air, which is the same stuff?
You just said that the air up here is less dense than the air down here.
Yeah, but why is it like that? Why has that happened? Why is the air settled like that? Why is there that gradient of pressure?
Well, that's what we can observe. I mean,
yeah, we can observe it, but we need to ask the question why. Because if, and this is important, if we were in a dome and gravity didn't exist, then the pressure would be constant everywhere. At every point between the dome and the surface of the Earth, the pressure would be the same. Because actually part of the definition of gas pressure is to have an equal density throughout. But that's not what we observe in reality. What we observe in reality, is a gradient of pressure that goes to a near vacuum, all right? And there's no dome or container as you go up. Plus, I can actually show you high pressure sitting right next to low pressure. Very high pressure next to very low pressure without any kind of barrier. That's quite easy.
Really?
Yeah. Back to my favorite thing, nuclear fusion. Well, fission in this case, actually. Oh no, this is fusion. Tokamak nitrogen purity. So, I'm going to show you a nice little video. A little bit of a sidebar here. So what I'm showing you now is the inside of a nuclear fusion reactor called a tokamak nuclear fusion reactor. Okay, and you can see they've they've pumped in the plasma. So right now the pressure in this whole thing is pretty equal, right? But using some very clever electromagnetic and forces, they actually pull all of the plasma, which is ionized gas, into a ring. And you can see that ring there. Now at this point, that ring of blue is extremely high pressure. Everything else in this chamber is a near vacuum.
But you're manipulating it with electromagnetism?
Yeah, but where's the barrier? Where's the container? There's no container.
There's
just a force, right?
Here is that the point what you're trying to say is that you can have gas pressure next to a vacuum if there's something manipulating the gas.
Yeah, that's kind of my point there, right? Because I think we can both agree that this blue band, which they've injected a bit of nitrogen into it so they can see what's happening with a Z pinch, we can all agree that this blue band is extremely high pressure. Next to it, directly here, is a partial vacuum. It's, practically zero, right? And there is no physical barrier between them. All there is a force of some kind, right? You agree with that?
Yeah, so I get what you're showing me.
A force of some kind is creating that. So the question remains, what is creating the gradient in our atmosphere?
Well, it could be electromagnetism, as you just showed.
Well, we'd be able to measure that, wouldn't we? And we can't. There is no measurable electromagnetic force.
You couldn't just rely on gravity to do the work, right?
Not in this experiment, no, because gravity isn't part of this experiment, right? But gravity is a different thing, works on a much larger scale. And we know that Fg equals gm1 m2 over r squared, the mass of the Earth would be more than capable of holding the atmosphere to it, because gravity would create the force that does that. And as we're showing here, you can have that gradient, you can have that pressure next to lower pressure, if there's a force of some kind helping you. But without that force, at this point here, the entire chamber is the same pressure, right? So with no force being applied, all the same pressure. With a force being applied, pressure here, no pressure here.
That's actually pretty interesting, because then you could say, well, maybe we live on a flat Earth with no container and electromagnetism is holding down all the gases.
Exactly. We could say that, but that's easily testable, because we can measure electromagnetic fields, and we find no electromagnetic field strong enough to do that. Plus, not the atmosphere isn't an ionized gas. The reason this works in the tokamak fusion reactor is because plasma is an ionized gas. It's had the electrons ripped away from it, which means that it can react to magnetic forces. But the atmosphere isn't an ionized gas, so it's not going to react to electromagnetic forces like a plasma would.
That is really interesting. I think that's actually really fascinating.
Kind of, but all right, please don't fall for the straw man of asking to see a container for the gas pressure, because that isn't our claim. That isn't the claim of the globe. The claim of the globe is that we have a pressure gradient which is observable. And that's it.
I don't mean to. I'm not. Don't even. Yeah. Okay. Yeah, but I get you. Yeah. And I think there's. No, it's a straw man.
Yeah, it is a straw man. Oh, wow. No. Okay, I've had this argument with flat earthers 600 plus times to try and make them understand that
to me,
that is a straw man.
To me, honestly, I could see how it's a straw man, but I can also see how it's just a question, just people that are curious, like how do you explain?
Yeah, but now I've given you the bit of the knowledge behind it, you kind of understand it more, right? You're less ignorant.
But in my mind, I'm thinking about how that applies to a flat plane. but it is interesting.
So the next question to ask is what does cause that gradient in our atmosphere? Because it wouldn't just be a container. A container wouldn't cause a gradient of the same gas, right? So there has to be something being applied to it to do that. And what's being applied is the force of gravity. So what's your thoughts on gravity?
Well, pretty much this. I went over this with McToon. Is the experiment I like to look at is the feather and the Brian Cox experiment with the feather and the bowling ball.
Okay.
And you see that the feather and the bowling ball fall at the same rate, and when you look at it, you can look at it from different. I feel like you can look at it from two perspectives. You can look at it like that mass cancels out according to the equations that we do. Or you could look at it that the density in a vacuum is zero. Therefore, when the medium of density is zero, the feather and the bowling ball, both having different masses, fall at the same fall rate because of the medium of density, not because of gravity. So that's an experiment that I looked at that I'm like. I asked McToon about this, and what did he say? He said that mass cancels out, but that's pretty much all he said, I think.
Okay, I just want to show you.
That I don't know how to do math.
Did the same experiment a lot earlier than Brian Cox. They did the experiment on the moon. Let me just show you this.
Did the experiment on the moon?
Yeah. So this is the they're on the moon, obviously. And he's got a hammer and a feather, doing exactly the same thing as Brian Cox did, but he's on the moon. No, he talks for a bit about it. And then when he lets them go, boom. That there does two things, right? Not only does it demonstrate what we say about gravity, but it also disproves the moon landing being faked unless they were able to film this entire thing in a vacuum chamber of some kind.
Yeah, the moon landing stuff is I mean, I would have a lot of questions on that one, but I never knew that this video existed. It's pretty.
Mm-hmm.
But okay, the one, like the first question that comes to mind is, if you're in a vacuum, wouldn't they explode?
Who?
Like if you put two people in a vacuum, like on Earth, let's say you created a vacuum like they did with the feather and the bowling ball, wouldn't the person in the vacuum not survive?
They're wearing suits.
Okay, but how does this? I mean, those are some special suits.
Yeah, they are special suits. They're designed to be in a vacuum. So here is James May wearing one of these suits and going into a vacuum chamber. So he's in this chamber here, and you can see this bottle of water that's here just randomly starts like boiling as they reduce the pressure down and down and down. You see it boiling there. So there you go. He is literally in a vacuum chamber right now, and he's not exploding. And the reason he's not exploding is because he's wearing a suit designed not to explode in the vacuum.
That I've never seen. That's pretty interesting. But I just based off all the moon landing stuff I've seen, I'd have to assume that that they're lying in that video. Sorry,
Why?
my dog. Hold on one sec.
That's okay. All right, just give me one sec. Yeah, give me one sec. I just need to address the chat a sec. Some of the mods are going a bit heavy with timing people out. Can we not time people out whether they're a flat earther or not, unless they're being racist, abusive, you know, talking about things which we obviously know shouldn't be talked about. Don't just time them out for, you know, being a flat earther unless I've specifically initiated the Vicky treatment for them. Okay? Bite My Haggis isn't currently on Vicky treatment, so please don't be timing Bite My Haggis out. Yeah, there's a few mods that are going a little bit heavy-handed today. I appreciate you guys doing what you do, but please, I don't want my chat turning into, I don't want to be accused of having an echo chamber in my chat. All right, so obviously I'm not going to have flat earthers as mods, but I give my mods the responsibility to look after the chat. But that responsibility is there so that you guys can make sure my chat isn't going to get my channel shut down by people saying things that YouTube doesn't like. Please don't just time out because you don't like what someone has said. And if you're not sure if you should time someone out, then please either speak to me or some of the OG mods like Tommy Gronville and stuff. All right. Thank you. Sorry, just had to do that there.
Yeah, no, I mean that. Yeah, because I mean, but you see experiments when you put shit in a vacuum and they explode.
Yeah, because they're in things that aren't designed to withstand a vacuum. You know?
Yeah, there's just too many videos of the moon landing where it looks like they're being pulled up by wires, or even
That's
in
because
one
they've
of them,
got really low
you can
gravity.
literally see the wire.
Well,
What's
you know
that?
they had an antenna on the back of their suit, right?
Oh yeah, I know that, but there's moments where they're like on the ground and all of a sudden they just like lift off. They just get pulled up, and then there's one where they're next to the American flag and you can see the wire on the very top of the screen and him get jerked up all of a sudden. And so like when you see shit like that, you and then you can't trust
again, it's just the antenna, and the jerky motions is because they're not under gravitational effects that they are used to. Their motions aren't going to be normal, you know? It's not going to look normal to us, and it's probably not going to feel normal to them. You know, could you imagine just all of a sudden being in a place where you have 6 times less acting on you? You know, you weigh 6 times less. You can jump higher. You fall slower. Can you imagine what that would be like? You know, you wouldn't be able to act the way you normally would on Earth. Your movements are going to look weird, right?
Yeah, I mean, this is one of the things that I've actually like made some little short videos on because I just thought it was, I just thought it was hilarious. Okay. But hold on. There's, yeah. If we could share a screen, there's just like little 20 seconds of shit.
Yeah. And then we'll take a little break and read some super chats. There's a few questions for you.
Okay. So,
if you guys want to get any questions in for Scott, either tag me or maybe try and post it. Ask Tommy to put it in the Discord or something, or send a super chat and I'll read that out first.
Okay. So.
Okay.
We're here. Okay. So in this one, let's see. Okay. So this one, you can see
hardly anything.
Yeah, not in that one. That one's not that good. You can see a little thing up there, but
again, they've got antennas on the back of their suits, which light.
I get that, but it's this next one. Hold on. Okay, this one. He gets jerked up all of a sudden. You see the wire. You see the wire up here. You see him get, boop, pulled up, and all of a sudden his feet lift up, like he got pulled. And then this one...
I didn't see the wire. I'm sorry. Where was the wire?
Up here, where the hand is pointing, you can see a little flash.
Yeah, that just looks like an overloaded pixel of some kind.
It could be seen as the top of the wire that they didn't cut out.
I mean, like I said, they've got antennas directly on the back, and sometimes if there's like a line where the camera's looking at, you know, where it's
this guy gets pulled up, like he's here and then pulled up.
No, he pushed himself up. You can see he's on his knees right now, and he pushes himself up. And because
without
there's
any
less
arms?
gravity, he's got his arms on the floor right now, and then he pushes up. Plus, the other guys seem to be giving him a good bit of help.
And then it's like, okay, so then you look like the illusion of gravity until you speed it up 2 times speed and insert it in
Oh, yeah, no,
images.
you couldn't have had slow motion back in 1969. You know that was impossible, right? So, back then, the only way you could do slow motion is with a process called overcranking, where you would, double the speed the reel was going through the camera. You had to have a specialized reel. If you wanted half speed, you would double the speed the reel was going through, and then play it back at normal speed, and it would look in slow motion. But the problem was the cameras that existed at the time literally couldn't record more than like 30 seconds of slow motion footage at a time. The technology for that did not exist anywhere. So to do slow motion for the amount of time that they did full shots, the actual technology didn't exist unless it's some super secret technology that only the Illuminati have access to, of course. Illuminati, fuck's sake.
Yeah, I mean, to me, it's you watch the moon landing footage, and that's the proof that it was fake. I mean, to anyone.
But to me, it looks like it should.
Anyone with any kind of skeptical mind whatsoever is going to be like, no.
Yeah, but the thing is, anyone with a knowledge of physics will look at that and go, well, that makes sense. And again,
yeah,
I'm not being rude, Scott, but you're ignorant of physics. If you don't mind, can I ask, what is your educational level?
I don't have that much education, really. I went to community college for a couple of years, and in my young 20s, I was a party kid. I didn't give a fuck about anything. So,
what did you study at community college?
I took some music classes, and then I don't know. I never gave a crap about school. I never cared about the subjects really.
Right. I'm a guitar teacher.
So.
Interesting.
Yeah, I teach guitar.
Oh, so do I. That's what I'm saying. I am a guitar teacher myself.
Oh, nice. Yeah, it's fun. It's chill. Teaching guitar is fun, but yeah, I mean, I don't have a background in physics, but to me, it's like there's so much evidence, observable evidence, that we do not live on a ball.
Like what, though? Right, okay, there might be what you observe straight away, but none of the observable evidence holds up to scrutiny, Scott. Whereas all of the observable evidence for the globe holds up to scrutiny. And it goes back to my question of why isn't there any measurements of the Earth being flat or stationary? But there is countless measurements of the other way round.
Okay, hold on.
Right. We'll get to that question in a minute because I'm going to talk you through an easy experiment to measure the rotation of Earth. But we're going to read the super chats first. Right, so Folk Repair Shipakashi for $2 says, our senses are shit, spatial disorientation 101. Yeah, Scott, our senses are rubbish because according to my senses right now, you are an indistinguishable blob. See why I don't trust my senses?
I'm trying to find a source, sorry. Hold on. Yeah, I'm a blob, I got it.
Anon Adhom, I didn't say you can't do slow motion in 1969. I explained the process and the technology that existed. It was overcranking, and the ability to do slow motion in long takes like that simply didn't exist.
Is this the...
Okay. FastCat499 says, hey FTFE, love the show, keep up the great work. Hopefully YouTube will take down the real Simon Dan, aka Daniel Pratt for impersonation soon. I've got another video about Danny Pratt in the works, but you know my release schedule on videos is about as reliable as Amber Heard in a trial in court. So, Spud UK 78 chips for £5, 5 English pounds, says sometimes to get through a flat Earth debate I have to get so high I can see the curve of the Earth and my house. Don't worry guys, I'm always high.
I mean, we already went over how you'd have to be high to see the curvature over a lake, so...
Yeah. I mean, I am high all of the time, but, you know. Greg Ware, $2 Australian. Forget him, not us syndrome has taken over. That's flat Earth in general, Greg. Throw the dwarf of the House of Torg for $5 Australian. Yep, a very big pair of binoculars that can go that far like in Looney Tunes. Okay, yeah, I mean, obviously, looking through the atmosphere, you're going to get diminishing of what you can see. But when you're looking up at the stars, you're actually, for the majority of it, not looking through an atmosphere. So there's no reason you couldn't see for trillions of miles. Fokapeshi Pakashi, $2 Australian. Nope, just $2, sorry. Australia is not bigger than Canada for Venti's sake. Yeah, absolutely. And then $5. Pilots are busy people, Flerf. We tell you that the Earth is flat, so you get off our fucking flight decks. We have to keep you safe without distractions. What do you think about that? That's from a pilot.
Yeah, he's just, yeah, the Earth is flat.
Yeah. Here's the thing, right? If you're busy working and some nutter comes in your thing going, guys, is the Earth flat? You're going to be like, yeah, mate, can you fuck off? You know? Pilots will, and it's kind of a joke between pilots, you know, I've had several tell me this, that they like to screw with flat earthers. But when you actually ask a pilot about how they do their job, it requires the Earth being a globe. Eon Dust for $10 Australian. Serious question. Do you actually think it's flat, or are you just hoping it so you feel that you haven't wasted your time?
I'm always open to, yeah. I mean, I think it's important to be able to put whatever beliefs you have at any moment aside and look at anything. And there were a couple things I thought were really interesting.
Okay, so I mean, you're genuine in what you think. That's okay, because we do have a lot of pose, which are people that pretend to be flat earthers. Oh, sorry, just a flat earther in the chat. Truth is Criminal says Craig doesn't actually believe any of the crap coming out of his mouth. You see, it's all in the name of the god of Mammon that perpetuates this nonsense. You can shut me down. What the fuck are you on about, Truth is Criminal? The only god I believe in is the flying spaghetti monster. Bless his noodly appendage. Jake the Surgeon, $5. From what I've seen, Scott seems to be more polite than most Flerfs. Yes, Scott, you are not a colossal dick flute, so congratulations on that. Keith M for $5. Bloody hell, stop insulting those of us who teach physics again. Every time he is on, he insults those of us who actually studied teach physics. I think, so, that's from a physics teacher, and he thinks that what you're saying is insulting.
Yes, we all have egos.
Is it an ego if you spent your entire life studying a subject to become good enough at it so you can teach other people to, you know, get jobs and stuff by learning the things that you teach, to then be told by some guy on the internet, nah, you're wrong? Don't you think that you have a right to be a bit annoyed about that?
Okay. I don't claim to be, you know, I'm not a fucking concert musician, but I teach music theory in a really, I'm really good at teaching it very simply. So, because I'm teaching, you know, high schoolers and kids, right? So you have to explain it really simply. And if someone came along and was like, yo, I can teach, there's a way better way to understand music, let me show you, I'd be open to that. I'm not going to be like, no, I learned from this, I learned music theory for, you know, and I figured it out and it makes sense. Why can't you be open to it?
I mean, I'm open to anything. I've got a very open mind. That's why I tend to base what I do on science, because science has an open mind. Science will update its position if new evidence is presented, you know? But we're just waiting for that evidence, and it hasn't come yet.
Can I share screen?
One sec. Eon Dust, $10 Australian. Scott Honey, most people never have a full grasp on these things. Only those who are willing to dedicate their lives to studying it actually have a chance. Quick Google searches won't cut it, hun. I think they're telling you to go back to school there, but... Rachbot, hey Rach, how you doing? For $5 says, brilliant destruction as always, my lord. Calepsis, $5 says, fun fact, if the vacuum column was 500 miles high, the bowling ball would noticeably land first because its mass is greater than the feather. Yay, math. Eon Dust for $5 Australian says, MC Toon told you this and I'll tell you too. The universe is a complicated thing and it's under no obligation to be simple for you. That's very, very true. Right, okay, so you want to share your screen. Please go ahead.
Well, I mean, I don't, not that I trust the, you know, when there's like a published article in a respected thing, like, not that I ever trust that, but I'm just showing you that I did come across a study that does prove that the Earth is stationary.
You came across a study that proves that the Earth is stationary. So it wasn't science then, because science doesn't prove things, right?
Yeah, it was just a study. Hold on.
So, I mean, it wasn't a scientific study then?
It's from the Royal Society. It's about looking at light. Okay, hold on. The Royal Society. Oh, that doesn't really sound good. Why is my shit's not pulling up? Sorry, hold on.
That's all right. That's all right. You take your time. Indie Tigers Sci-Fi Review for $10. Thank you very much, dude. I was arrogant before I went to university for engineering too. University humbled me when I learned actual physics. Never a Flerf, mind you, because I navigated ships in the Navy before university. Yeah, you literally can't do navigation and be a flat earther. Pylo1408 for $10. Scott, we live in an age of scientific wonders. You're using some of them to talk to FTFE right now. You should look into some of the things humanity has accomplished by going beyond common sense. Tesla Bitten for $5 says, Scott, without a foundation of a subject, you would not be able to understand the advanced parts of the subject. I see it every day in the radio field. We call it the Dunning-Kruger effect. Right. You got that study?
It's not letting me pull, like, for some reason my computer's not letting me, like, God damn it. It's not letting me pull up Zoom. But
if you send me a link to it on Facebook Messenger, I'll bring it up.
All right, yeah. Shit.
Technology. Just take a quick break and ask Quantum Erasure how he's getting on. Quantum Erasure, are you there? How you been getting on, dude? Hello, Quantum Erasure.
Bagaki. I'm an idiot. I'm a stupid moron with an ugly face and a big butt, and my butt smells. And I like to kiss my own butt. I'm an idiot. Bagaki.
The ever eloquent Quantum Erasure there.
Okay, I sent you the study. I'm still trying to pull up fucking Zoom.
Okay, let's read this together, shall we?
Oh, I got it back.
On a supposed alteration in the amount of astronomical aberration of light produced by the passage of light through a considerable thickness of a refracting medium. Abstract. A discussion was taking place on the continent, conducted partly in the I'm not going to pronounce that, party and independent pamphlets, on the change of direction which a ray of light will receive when it traverses a refracted medium, which has a motion of translation. The subject to which attention is particularly called is the effect that we produced on the apparent amount of that angular displacement of a star or planet which is caused by Earth's motion of translation, and is known as the aberration of light. It has been conceived that there may be a difference in the amount of this displacement as seen with different telescopes, depending on difference in thickness of their object glasses, blah, blah, blah.
We could look at something more fun.
Where does this say that it shows that Earth is stationary? I mean, it doesn't.
You have to like.
That.
Okay, so I shouldn't have linked that because you have to download the fucking study. But I can show something more fun about.
Okay. Yeah, go ahead.
About it has to do with the stationary Earth and kind of
Yeah, is it a measurement of Earth being stationary?
It's just a.
Oh God, it's P-brain.
Oh yeah.
Right.
Okay, so this is.
He's one of the dumbest flat earthers that exist. You really shouldn't be citing him.
Okay, but I don't give a fuck who put this up. But this is just something I thought was interesting. Okay, because if the Earth is spinning 1,000 miles per hour, the person in
the Earth isn't spinning 1,000 miles an hour. That's not a thing.
You want to use degree? I'm American. That's how I think. I don't know how to think.
The Earth is spinning, 0.000694 RPM, which is half as fast as the hour hand on a clock. The surface of the Earth at the equator moves at 1,000 miles an hour. The Earth isn't spinning at 1,000 miles an hour because you can't spin in miles per hour.
Okay, well, I'm sorry, but that's the only way that I can think about it. Because
I mean, it's the wrong way to think about it.
Okay, this is the only question I have is...
Yeah, go ahead.
So if you're spinning 1,000 miles per hour on the equator, you're not spinning at 1,000 miles an hour, say, in Alaska.
Yeah.
So if a plane lifts off and flies down to the equator, how is there... there should be a radical difference in wind, wind and the moon.
No, not in wind, because the wind is atmosphere, which is moving with the Earth. I mean, this entire graphic is completely wrong, because every single section of that should be rotating at the same speed.
But if you're on a ball, it's not going to be the same speed, right?
It is. Every single section of that ball is going to be spinning at 15 degrees per hour. There's not going to be different sections of the ball moving faster than the other sections. It all spins at the same speed. That just means that the tangential speed at different points is faster. That graphic shows the Earth literally moving at different speeds, which isn't the case. It's all connected. It's all one thing.
The people that are living in Alaska would not be rotating as fast, right?
They'd be rotating at exactly the same speed. They'd be rotating in 360 degrees over 24 hours. So they're rotating at the same speed. But the tangential speed at the surface is different, right? So just imagine a basketball spinning on your finger, right? The entire basketball is spinning at the same speed, right? But the equator has a faster tangential speed than the point that's touching your finger. But the whole thing still rotates once in 24 hours. So the rotational speed at every point on Earth is exactly the same.
That actually might have been a bad example. I haven't really.
Yeah, it was. That you really shouldn't ever bring up P-brain. He hasn't got a clue what he's on about. Like, even other flat earthers think P-brain's a fucking moron.
Well, that's good. I'm learning.
So, right. Here's the thing. There's no measurements of the Earth being stationary, but it's dead fucking easy to measure the Earth rotating. How easy, you say? Well, a flat earther did it, right?
Oh, you remember the gyroscope and all that, yeah.
If the Earth is spinning at one rotation every 24 hours, that means that every hour it has to turn 15 degrees. And if the gyroscope is mounted anywhere on Earth, it's going to drift. In today's 21st century navigation systems, they're using what's called a ring laser gyroscope. It is extremely precise. If we could simply get one of these ring laser gyroscopes, we would be able to prove once and for all that there is no rotation to the Earth. One of the people in the community actually purchased one for $20,000. But what we found is when we turned on that gyroscope, we found that we were picking up a drift.
How much of a drift, Bob?
A 15 degree per hour drift.
Oh, thanks very much for that, Bob. Thank you.
If the Earth is spinning
very
at
helpful.
one rotation.
Yeah. So now, obviously that's from a Netflix documentary. It's edited to be pretty and shit, but it doesn't change what he did, which was measure the rotation of Earth. And interestingly, it works everywhere. He then took that gyroscope I've got a video that is actually one of the most popular on my channel, where him and Nathan Thompson are playing with that gyroscope in his house, showing how they just turn it on and it registers a 15 degree per hour drift, right? Now this is a fiber optic gyroscope, right? It uses light. So they started trying to say, oh, it's affected by the heavenly energies, blah, blah, blah. Even though light isn't affected by electromagnetic signals because it's got, no charge. So after that happened, the team at Globebusters commissioned an engineer, a flat earther engineer called Stephen P., to build a mechanical gyroscope. Because they were convinced that, the mechanical gyroscope, that's going to show that the Earth doesn't rotate. All right? So after using the laser gyroscope, Stephen P. built this marvel of technology. Very impressed from a flat earther. What do you think happened when they spun it up?
I mean, it's going to measure a 15 degree drift, yeah.
Absolutely. They tried changing the axis of rotation, pinning down certain sides, and every single experiment they did with this mechanical gyroscope, no electronics in sight, showed that the Earth is rotating the amount that fiber optic gyroscope said. And do you know what they did? Do you know what Globebusters did? They tried to sue Stephen P. and tried to get this video banned and taken down from everywhere. Why would they do that?
Well, I mean, there's two sides to every story, you know.
Oh, they admitted that they didn't want it out. They said that he was lying and stuff, but, the proof is in the pudding, and it's something that anyone with a bit of engineering knowledge can do, build a bloody gyroscope, But,
okay, in the documentary when they do the laser test, with the boards and all that.
Gyroscope thing.
Yeah, I mean, because if you listen to the other side of the story, they tell you that it's like the conditions were really bad. It's like everyone there was in agreement that the conditions were too bad to determine anything.
I mean, they still saw the light,
and they cut it before they saw the light. So
no, they saw the light when they were looking through it. They set it all up.
They actually saw.
I mean, they set it all up, and then they filmed looking through the holes, and they couldn't see the light, so they asked the guy to lift it up, and then they saw the light. They tried to say that it was deceptive editing, and it was all backwards and stuff, but there's no evidence of that. And in fact, I've spoken to the director of that show, personally, and he says, no, it wasn't deceptive editing. This is the order that we filmed it in. So, I mean, I don't know what to tell you, but... well, I do know what to tell you, Scott, and that's that flat earthers lie. All right? Flat earthers lie all of the time. In fact, it's a meme. Hashtag gotta lie to Flerf. Because you can't push the flat earth. You can't be someone like Gyroscopes and still think the earth is flat. When he himself has measured has seen the ISS crossing the moon. He himself has seen the curvature of the Earth.
I mean, even the lenses. I mean, let's say any kind of rocket goes up. Oh, let's put a really fish-eyed lens on that. You're lying to people about what it actually fucking looks like.
No, you're not lying. Fisheye gives a wider angle and a pretty view.
You're purposefully distorting people's view.
No, here's the thing. They don't put those cameras on to prove anything to anyone. They put those cameras on so they can monitor the rockets in space and get a pretty view. All right? All of space industry, NASA, Roscosmos, JAXA, SpaceX, whatever, they don't care what you think. They have no interest in ever proving anything to you because they already know space is real because they put stuff there. So they don't care what you think. They're not lying to you by showing you a fisheye camera. They're just putting a fisheye camera.
Well, that's a fucking asshole thing to do, to distort people's perspective of reality.
But no, again, they just want a pretty view. They're not trying to say
pretty if you don't curve it.
Well, a fisheye lens can give you a wider angle. You can see more, right? It's got a bigger field of view in general, right?
It's the illusion that you're in outer space and you're...
But they're not trying to fool anyone. They're not doing it to try and fool anybody. They don't care what any of you think. Because their job isn't to prove anything to you. They don't have to answer to you. They've got no obligation to show you exactly what the Earth looks like when they go to space. They've got no obligation to do that to you at all.
The public has a right to know what the Earth looks like.
Yeah, and they put out plenty of stuff that shows what the Earth really looks like. But they are under no
footage has to go up without the bullshit of NASA to show us what it actually fucking looks like.
Yeah, they did. I showed you the video of that earlier.
Yeah, and it looks flat as fuck, and the horizon does not do what it does on a fisheye lens.
It showed a curve without a fisheye lens.
In one image.
What, when you're up high enough to see it, it shows what you expect to see.
Most of it looks flat. It's just...
It really doesn't. There's a curve there. As when you get high enough, you see the curve.
The point is distorting people's perspective of reality.
But they're not distorting people's perspective because they're not trying to say that's exactly what it looks like. They're not lying to you. They have millions and millions and millions of pictures of the entire Earth. In fact, there's every 10 seconds there's a new picture uploaded from Himawari. You've got Discover satellite. You've got satellites out at Lagrange point 1.
If I go to Google right now, I type in outer space, I'm not going to see only cartoons and CGI.
No, you're not going to see only cartoons and CGI. You're going to see a lot of CGI and artist impressions, but you're not going to see only that. But also, Google isn't NASA. So what does that matter?
Google, I mean... Yeah, if you don't
Google
think
isn't
Google
NASA,
is
dude.
fucking with
Google
the algorithms, I don't know what to say.
Google simply shows you the most popular things, and it's usually pretty pictures.
They show you what they want you to see.
Well, that's why there's ads in usually the first 4 results. That's what they want you to see, to click on to get money.
Why don't you go to Google and type in, are vaccines safe? Let me know if you find a single fucking link to someone with a different perspective than the narrative.
Yeah, but vaccines are safe. We know that for a fact, so, you know.
Oh, good. Yeah, sure.
Yeah, we do. We know for a fact that vaccines are safe and save millions of lives all the time. Hey, you know polio? Oh, wait, that's right. Vaccines got rid of it.
Polio? Yeah, okay. What? You obviously did not look at any other information.
Polio doesn't really exist anymore because, we wiped it out with vaccines.
It's just...
How many people do you know that get measles, mumps, or rubella? No, because we kind of wiped those out with vaccines.
You know what VAERS is?
Yeah, theirs is a unverified reporting thing for anything. Anyone can put anything they want on that. Okay.
And guess what? That's the only reporting system for adverse events there is, and you said it's a fucking joke.
Incorrect.
So there's no fucking system.
Incorrect. It is the incorrect.
Doctors and nurses.
No, you are incorrect. But we're not going to go off on the vaccine talks because YouTube gets angry about it.
I know.
Okay?
You might get. I know.
Right.
I know. I went down that rabbit hole hardcore. I could link a lot of fucking studies to that shit.
Yeah, and I can debunk every single one of them, which I always do. Telsa Bitten, $5. No, read that one. Triple Crow H has been a member for 9 months. Says, is every physicist in history lying or just dumb?
They're brainwashed and indoctrinated.
No, they study things. That's nothing to do with it. They don't care what people say. They study the universe and
they were told they live on a ball since before.
No, they figured it out. Most of them figured it out themselves. I told you how education is not indoctrination. Education, when you actually go and do it, Scott, is something that gives you the tools to figure these things out for yourself. It's how I knew how to measure the rotation of the Earth. It's how I knew how to do the calculations for fuel consumption, because I went to school and studied. It's not indoctrination, it's giving you abilities and tools to do something. The only people that say education is indoctrination... No, the only people that say education is indoctrination is people that do not have education. And that is a fact.
That's not a fact at all.
No, it is. People that are educated do not think education is an indoctrination. No one that went and studied physics thinks they've been indoctrinated. No one. Because they can prove to themselves what they say, thanks to their knowledge of physics.
based off assumptions and theories that...
No assumptions. I mean, science requires assumptions, but, you verify things by doing experiments and stuff and try and disprove hypotheses. Do you know the scientific method?
Well, I know there's some basic stuff. You gotta observe it, which seems to not be the heliocentric way
No,
to do things.
that's always the start. You make an observation.
Yeah.
Right. Yeah,
and
what's
then,
the next bit?
you measure it and you repeat it.
No, that's not the scientific method. Who told you that rubbish?
Well, there's several steps, but...
Well, what's the 5 basic steps you would learn at high school?
I don't know what you learned in high school. No.
Well, what anyone that did science. I'm assuming you went to high school and you did science, right?
I never paid attention.
Right. That makes Scott. That's why you're a flat earther, mate.
That's because you subconsciously know when you're being fed a bunch of bullshit.
No.
Like watching the news.
You don't know anything. That's why you are a flat earther, right? When you listen at school and you're studying science, the basic method that they teach you is you make an observation and then you form a hypothesis about that observation. And then you make a prediction with your hypothesis and then you design an experiment to test your prediction and then you analyze the results in an attempt to falsify your hypothesis. All right? Flat Earth never does any of those. Only people on my side do that. Why is that?
I mean, you're asking someone that doesn't have a background in that stuff, but I'm sure there's plenty of flat earthers that wouldn't have a great answer for that.
Well, I've debated over 600 and none of them ever have.
Not according to what... You see something wrong because it's not what you're taught, but...
No. I mean, no flat earthers ever been able to just, demonstrate that they understand the scientific method, And if you're not following the scientific method, then you're not doing science, are you? But using the scientific method, and the reason I've been badgering about measurements is because I've shown you 2 measurements of the Earth rotating, right? So what if I could show you a third one that backs that up? I mean, is that repeatable enough for you?
I mean, I have to take my time to go through those later, but yeah.
So, have you ever heard of Foucault's pendulum?
Yeah.
Right.
Yeah, I mean, I've heard of it.
Well, Foucault's pendulum is an amazing way of measuring the rotation of Earth because it allows a pendulum to swing freely, and whatever the pendulum is on, it is going to move around underneath it. So if you've got a roundabout and you put a big pendulum on that, roundabout. If you've got a merry-go-round, you call it in America, and you put a pendulum on that merry-go-round and you're spinning it, and you start swinging that pendulum, the swing will stay in the direction that you've gone. Even though the entire apparatus is turning, the actual swinging bob will stay going in one direction, right? And you can use that principle to measure the rotation of Earth. So it's very, very simple. A guy called the Gentleman Physicist, this dude, made his own Foucault's pendulum in a high-rise building, right? If the Earth is rotating like we say it should, like we say it does, then as the pendulum swings, it's going to drift. There's going to be a change in the direction of that swing if the Earth is rotating. And the amount that drift will correlate to your latitude on Earth, right? That's the prediction that we would make using the scientific method. So what he did was he let the pendulum swing, and as you can see, it's going through this ink pad and drawing a line, right? And they let it swing for as long as they can. I think it swings for about 45 minutes, so they need to figure out how long it would take to do one full rotation, and they find out that it would take about 30 odd hours to do one full rotation, right? So what they do is they leave it swinging for 45 minutes, and you can see how it's no longer a straight line, right? So what they do is they take the angle, it's turned clockwise, which is what we expect in the Northern Hemisphere, and they take the angle that the drift is, which in this case 7.89 degrees, right? And they take the final time of 6.88 hours, which is about 45 minutes, and you can calculate how long it would take to do one full rotation, which is 31.4 hours. And then if you use Foucault's sine law, which is a correlation between the circumference of the different latitudes as you go around the Earth and how fast the Earth is rotating, you can actually use the amount that pendulum has drift to calculate your latitude on Earth. So you take the arc sine of 24 hours divided by your period of rotation, and you can calculate your latitude on Earth. In this case, they get 49.8 degrees, which is less than 1% off of their actual thing. 1.4 degree error, right? Really fucking good. And this works anywhere in the world. There's the same experiment that was done at the South Pole, and they got 24 hours as a period of rotation, which is what they expect. But the most important thing, Scott, is that this matches the predictions of the globe model, and there's no explanation at all, if the Earth is flat and non-rotating, as to why the amount it drifts will correlate to your latitude on Earth. It's an exact correlation every single time. There is no electromagnetic force that could cause that to happen. And you can do the pendulum with different materials anyway, so that, destroys that. But there's no reason this happens if the Earth is stationary. It's a direct measurement of the Earth rotating. What do you reckon?
That is one I'd have to look into. It looks, it didn't blow my mind, but it is something interesting.
Well, it's something you can repeat yourself. Anyone can do it. In fact, I'm in the middle of trying to get it done myself. In Dunfermline, there's an old fire station, which is now a museum, and it's got like the big fire tower, and I'm in talks to use that to do my own experiment to see if I can calculate my latitude on Earth, right? But there's no reason for it to happen if the Earth is stationary. There's none. It is a direct measurement. It's as direct as you standing on a set of scales and getting a measurement. It's empirical. It's repeatable. It follows the scientific method. It matches the predictions.
Yeah, it's just like when I compare, like if I compare the evidence to, it's like, it just seems like there's a lot more powerful evidence on the other side, but
what's more powerful than a direct measurement? Nothing is more powerful than a direct measurement. An empirical, repeatable, direct measurement that matches the other two that I've shown you, done by flat earthers, that still measured the rotation of the Earth. And here's the thing, Scott. Every single attempt to measure the rotation of the Earth ends up with a measurement of the rotation of the Earth. They never find out that it's stationary, ever. Airy's failure failed to detect the aether and showed the Earth was rotating. The Mixon-Morley effect failed to detect the aether, and the entire experiment was based on the fact that the Earth was rotating, and verified that fact. And these are hundreds of years ago. Anyone can measure the rotation of the Earth. And the brilliant thing about the pendulum experiment is that it doesn't only show that the Earth is rotating, but because the amount of drift correlates to your latitude on Earth, it also demonstrates the Earth's a globe. Because you've got this equator where you would get no drift, and you go up to the north and it gets more, or you go down to the south and it gets more. That only happens if the Earth is a globe that is rotating. What else do you think could cause the drift of the pendulum?
I don't have an answer for that one. Sorry.
Only the rotation of the Earth, Scott. Only the rotation of the Earth. Scott, I'm going to save you. You are not going to be a flat earther. All right? You don't need to be. You don't need to be a flat earther, right? Because...
Well, I will tell you that I will put flat earth aside and I will look at shit. I know I talked about refraction, and I'm like, that one is definitely leaning towards not being what it says it is, but I still haven't done the homework. I know that, so... but it does...
I think you're early enough that we can save you. If you just try and verify these things yourself. You know, actually look into the results rather than just listening to what a conspiracy person says and believe in that. Actually look into it deeper, you know, into experiments, into verifiable empirical evidence, because it exists everywhere. It's easy to find. MC Toon's got most of it on his website. Seriously, any homework you want, just go to mctoon.net.
Yep.
Bite Mahaggis, you say, no, it's not a fact, Craig. Some people who have gone through the education system and have the ability to break their programming and see what it is, pure indoctrination. Bite Mahaggis, you never went through the education system, so you can't say that.
I do have a friend that got like a music degree in college, and I mean, I can run circles around him. So it doesn't really always mean that much, but he didn't understand it at all, but it's okay.
A few more super chats. Let's see if there's any more questions for you. Jake the Surgeon for $5 says, if I showed you the skeletons of a lion and tiger, would you know the difference with just layman's knowledge?
It's not my expertise.
So no. I think his point is you need to study things to understand them properly. Obi-Wan... Sorry, go on.
Oh, so if someone like finds like one piece of bone and determines it's an entire animal, that's pretty... I'm going to question that.
People don't tend to do that. Obi-Wan for $10 says, Scott, MC Toon asked you to take some time to learn about refraction. It appears that you ignored that advice.
I didn't have time. I was working, and he asked me on late last second.
Yeah. To be fair, this was a last-minute thing for Scott. The guy I was supposed to be debating bailed. The guy I was supposed to be debating bailed, and Scott, like the nice guy seems to be, stepped up, and I appreciate that. But Scott, definitely look into refraction, and please send an email to Andrew Thomas Young. All right? He will happily speak to you about refraction, and he is the world's leading expert. Graham Price, who's been a member for 26 fucking months, says, Scott, you've been lied to. Please just accept it. Flat earthers always lie.
I mean, the heliocentric model seems pretty far out there.
I mean, it's verifiable, though. Yeah, that's the thing. Just because it seems far out there doesn't mean it's not correct. That, again, is called personal incredulity. Fog Repair Ship Akashi, $2 says, who are they and where is the Aluminium Falcon then? Aluminum Falcon? What?
Millennium Falcon?
He said, he typed aluminium. I think it's a joke I don't understand. I'm sorry. Calypsis for $2 says, gotta go watch the new season of Westworld later. Keith M, $5. Again, he continues to insult those of us who do the studies and do the work. The man promotes how dangerous crap. This man promotes dangerous crap and needs to not be platformed again. I'm going to save him. Don't worry. Scott, I'm going to save you. Pilo148 for $5. Scott, if people could determine truth on instinct with no knowledge, doomsday cults would never be a thing. I can actually demonstrate to you, Scott, how Flat Earth meets all the criteria for being a cult.
Well, they have a lot of strong evidence.
No, there's no strong evidence that holds up to scrutiny. In fact, there's no strong evidence, and there's no evidence at all that holds up to scrutiny.
You don't think it's strange that there, with all the observations of seeing way too far, that the answer is it's not really there?
Well, sorry if you don't like the answer, but the answer is refraction.
The answer is far out there, and if you're going to say that, you need strong evidence to back it up.
We have quantified and verified refraction. We understand how refraction works. We can demonstrate how refraction works. We can measure the temperature and density of air and show what we expect refraction to do, and it matches our predictions. So, that is pretty good evidence. Refraction is the answer to why we see too far. And it's part of our model. That's the important thing. If you want to try and attack the globe model, you need to also attack refraction as explained in the globe model. Otherwise, you're just strawmanning it.
It seems like... that's all right.
Christopher Mendez, $2. Show him sightings of Starlink satellites. Yeah, you can look at Starlink satellites. You just get an app on your phone. It shows you when you can see them. Quite often. Marty Mad Scientist, $5 Canadian. 2 hours smoking weed. Awesome entertainment. Face stuck to keyboard. Wee! Cat Stevens was a Flerf. Ooh, Coloricious was a dog a donut. I think he's high. Thanks for watching, dude.
Sounds pretty hot.
Fogger Persia Bakashi, $2. Look up Robot Chicken, the Emperor's phone call. That is fucking hilarious. Right, Scott, we've been going for over 2 hours now, and I'm quite tired, and I've had a migraine most of the day.
I don't have much more to add.
That's right. Maybe we can pick this up another day once you've had a time to look at some of the evidence. You've spoken to both Toon and I, so maybe we can arrange a time to get you to speak to both Toon and me at the same time.
That sounds like I'd have to bring someone else to back me
up.
Hey,
you'd be welcome to, but this is more about help, Scott. Right? I don't want to do this to argue with you. I think I can help you. All right, and I'm not being pedantic. I'm not talking down to you. You know, I'm saying that I could genuinely help you understand the reasons why you think the Earth being flat are wrong. And I can do that because I've studied. I've got a degree in physics. I've got a degree in nuclear engineering. I've got a BTEC National Diploma in Popular Music and 4 A-levels, you know. I can explain to you the reason why you have fallen into this rabbit hole of thinking the flat Earth is a legitimate thing. Because it's not. It's full of lies, misconceptions, and straw man. There is not one flat earther who can actually argue against the globe without straw manning what we say to be the case. And that's why they're flat earthers. Because they don't understand the globe model. They don't understand what we say to be true. If they did, they wouldn't be a flat earther. And you're going to be an ex-flat earther. In fact, I might see if we can get ex-flat earther Ranty to come and speak to you.
It would be fun to do this again.
Well, thank you, Scott, for coming. I really do appreciate it. I think we got through all the super chats. Have you got any final thoughts before we shut down for the night?
I got nothing.
Well, thank you very much for coming, Scott. I do appreciate it. If you guys want to see Scott some more for some reason, then he was also on MC Toon's channel. And we'll try and get him back on again soon. Well, thanks for coming, Scott, and we'll speak to you again.
See ya.
Take it easy. Well, there we go, guys. Ignorance makes a flat earther. That's it. How to be a flat earther? Be ignorant of physics. Just like Bite My Haggis in the chat. There's a reason Bite My Haggis won't ever come and debate me. That's because he's been in my debates and knows that I can destroy them. Golden Knight says, pole dance time. No, bedtime, my friend. That's for sure. Alright, guys. I'm going to work really hard to try and get a new episode of Flerfs Idiots out before the end of the month. Then I've got my collab with Brainy. Got a collab with MC Toon that'll be coming up soon. More debates. Launch of FTFE 2.0 with my Kickstarter for my documentaries coming up. Things have been a bit slow going with constant illness and stuff that I've been going under, and mental health issues that I have to deal with daily because I'm in pain and I struggle. So I want to take this opportunity to say thank you to every single one of you for the support that you give me. It blows my mind that there'll be 700-800 of you coming and watching a debate of mine, sending me super chats, showing me the support you do. From the bottom of my heart, thank you very much. I'm never, ever, ever going to paywall my stuff. Everything I do will always be free because I love doing it for you guys. The support is amazing, and thank you to every single person that supports me by watching the channel, by super chatting, by being a member, or by being a patron. Thank you to my mods for doing a great job. Even if you were a little heavy-handed today, please just chill out. I think I'm going to speak with a few of the mods and maybe come up with a set of rules that everyone has to follow if they're going to be a mod. But that's it for tonight, guys. Thank you very much for watching. I've had a good time. I hope you have too. And I will see you all soon. Remember, stupidity is not a right. Fight the flat earth. Fight the flat. 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 Good night, all. Thanks for watching.